Good morning, everyone. Welcome to the Mind the AirGap talk. Thank you for waking up so early. So, my name is Pedro Umbelino. I'm a senior security researcher at Checkmarks. There's my contacts there, email, IRC, Twitter. My main responsibility at Checkmarks research team is to research whatever I want, which is pretty cool. So I have to thank Erez and Yalon for that. It's a great team to be working on. So what's this talk going to be about? So I'm going to talk about AirGap cover channels, data exfiltration methods, some examples, what's been done, the research that has been done in the past and now. And I'm going to present, hopefully, 2 live demos about NFC and Bluetooth low energy smart bulbs, and let's see how it goes. So why this need to research into AirGap? So nowadays you see that organizations and buildings have increased their security. There are more and more high security environments. So there's this need to investigate into new data exfiltration techniques. This could be out of the need to have a low fingerprint or have stealthy requirements. So there's these new techniques to exfiltrate data that are not detectable by current intrusion detection systems or needs. This can also be a method to evade or bypass low permissions. For example, there's some malware that's inside the system that cannot use, let's say, the Ethernet card or the Bluetooth card. But there are still some things that the hardware can control, like the access to the hard drive and make a LED blink, for example, and use that as a channel to exfiltrate data. And it's extra challenging. It's really fun to do this kind of research. I think it speaks to the heart of what a hacker actually does in the ways that it subverts the system and is able to control and have an effect, sometimes a physical effect on the real world. And you'll see in the examples, for those who are not familiar with the topic, that Hollywood has nothing on us. There are some examples that are pretty far out. So, boring part first. So what's an AirGap? So AirGap is a measure or a set of measures that ensures that a secure computer or system is physically separated from an unsecure network. So the name arises from this conceptual AirGap that exists between the 2 secure and unsecure networks. So in theory, the concept represents the maximum security that a network can have from one another. Of course, this is just theory. It's a theoretic concept. It's very hard to implement. Applications where AirGapping are seen most often are military or government computer networks and systems, some financial computer systems, some very industrial control systems like nuclear power plants, medical equipment, aviation, and SCADA systems, etc. So the definition for a cover channel could be defined as an unintentional channel that is used to transmit or receive data between systems in which AirGapping measures were taking place. So what I mean by unintentional is that the channel was not originally designed to transmit or receive data, but it's still used in that way. Although there might be some additional software needed at the target system, usually there's no hardware modifications at all. It's not like to bridge an AirGap that an attacker goes and plugs in, for example, a USB Wi-Fi card and then it bridges the AirGap like that. It's kind of a cheat. So, cover channel supports for AirGap. There's physical media. For example, Stuxnet used the USB stick to infect AirGap networks and then gathered all the information and recorded back to a hidden file system in the USB pen and then exfiltrated the data out. So that's a physical support for an AirGap cover channel. There's also acoustic supports. A computer can generate noise not only using the sound card but also the computer fan, for example. There's also light supports where a malware can blink an LED or a computer screen, for example, and use that as a support to exfiltrate data. Seismic. Nowadays smartphones have vibrations and vibration sensors that can be used, also magnetic thermal system, thermal supports, electromagnetic supports. There's a wide range of supports that can be used. I think imagination is the limit for this. So let's look at some real-world examples. So it's hard to talk about the air gapping theme without going back a bit to the Tempest area and talk about Van Eyck freaking. In 1985, Van Eyck discovered that CRT monitors emit radiation that is found very similar to television transmissions. So we set up an antenna and figure out a way to, just by pointing an antenna to a CRT screen, to actually decode what's on that screen. And he did it from 200 meters away. Later on, Marcus Kuhn was able to do it with LCD screens also. So there are many examples. We cannot go through them all because we won't have time for the demos. But some known ones are cool ones, like Lottery and Umpress devised a malware in 2002 that used the caps lock blinking at a very fast rate, and they were able to exfiltrate data out of the LED from the caps lock light. Sound emissions. Enspass and Goetz in 2013 created an acoustic mesh network where the computers used only the sound card and the microphone to implement a network. So the computers didn't have to have a Wi-Fi or an Ethernet card to communicate between themselves. They only use the sound cards. Now, state of the art. If you go to search this topic on Google, nowadays it's almost impossible to not be referred to the Ben Gurion University. So they are doing a lot of crazy research. For example, GSMEM. Anyone has heard about GSMEM? GSMEM is a software that uses executes memory instructions, memory move instructions, which actually turn your laptop into a GSM station. So the frequency that they get executed emanates electromagnetic radiations and turns your laptop into a GSM station, which can be picked up by a cell phone. They did the same with AirHopper. AirHopper turns your computer into an FM transmitter that you can pick up on your radio and exfiltrate data that way. They use USB. They turn the USB bus into an antenna by executing several USB commands. The principle is the same, generate some electromagnetic perturbance that can be picked up by a receiver. Traumashammer and Genking in 2014 devised an acoustic crypto side channel attack, which they used ultrasonic microphone directed at a computer, and they were able to pick the ultrasonic noises that the capacitors on the motherboard do when they are decoding some kind of information. So they were able actually to extract an RSA key just by measuring ultrasonic noise on the capacitors of a motherboard. Which is pretty cool. Bitwhisper. I'm going to tell you about this one. So at Ben Gurion University, they did a demo also, which was pretty cool. So they infected a printer scanner, multifunction printer scanner, and they devised they built a drone with a laser and a high resolution camera. So what they did was they used the laser from the drone. The drone was like 1 kilometer away, firing a laser into a building where the printer scanner was. And the scanner would turn on and receive the laser, was able to perceive that the laser was being shined on the room. So you have a downlink channel, and then blinked is a LCD screen. And the camera on the drone picked up the blinking, so you have an uplink channel. And they used the printer scanner to pivot in the network of the building. It's pretty nice. So there are a lot of examples. There's no time to go through all of them, but they're pretty cool. So now I'm going to talk about the data exfiltration research that we have been doing. So this is a tale. This is a light bulb tale. So I like to research stuff, random stuff. Sometimes it's even security-related stuff, which is cool. It turns out that I'm not alone. David Sopas, which is a colleague of mine, shares the same illness. I'm pretty sure most of you also share this illness. And David is nowadays researching a lot into IoT devices, and that's when he's not overseeing a bunch of crazy researchers like myself. Some months ago, he told me that he had a light bulb. He wants to hack into this light bulb, and the story begins like that. So plan A is always get root, right? He was not able to get root. There were some issues. There was not enough time also. But he was still able to do something. He was able to control the light itself on a light bulb, which is over there. So it's a RGB light bulb. So we were very surprised to see that there was no authentication at all in the light bulb. Everybody can control it. So there's this basic Bluetooth low energy security fails that if you go into BLE, you know. So the process begins with enumeration, endpoint enumeration, then figure out which characteristics in the light bulb were able to be written to, reversing the Android application to figure out the communication protocols and which codes control which channel on the light bulb and so forth. And then you have RGB color set at your disposal. So this is about the time when he called me and said, okay, I have no more ideas, what can we do with this? And I immediately thought, okay, let's implement a AirGap covered channel exfiltration through a light bulb. And say, okay, so what's our idea for implementation? So the transmitter was implemented using a simple scheme, just by changing the blue light intensity on the bulb. It's a little bit weaker for binary 1, a little bit stronger for binary 0. The blue channel, we chose it because the human eye has more issues distinguishing between the different shades of blue. It's just how our eyes work. So the protocol is really simple, just sends a preamble, then a byte, then a trailer. And we chose to cycle the colors in a slow manner because we wanted to use off-the-shelf components for the receiver. So if it changes in a slow manner, you can use the camera from any smartphone to receive that information, and you don't have to devise some kind of sensor to have a high-speed data exfiltration. So our idea is always to use low-cost off-the-shelf solutions that you can actually replicate at home to the POCs. So this is the attack scenario. Let's imagine that this device has been compromised by malware, and the malware steals user credentials. So the malware wants to leak this information, but the attacker wants to do it in a stealthy way or cannot use other resources like the Wi-Fi or Ethernet card or GSM or whatever reason the attacker chooses to. He wants to use a more stealthy way. Also, Bluetooth low energy doesn't have a very long range, and light, when it's shined on a room, can be picked up by a longer distance. So the attacker uses the Bluetooth to scan for nearby lamps. It discovers the vulnerable lamp and uses that lamp to exfiltrate data out. The attacker on the receiver end just has to point his device, his smartphone, to some area that's illuminated by the lamp. This is a very close setup that I have here for the demo. Let's try to make it work. First, I'm going to turn on the lamp. Hopefully, it turns on. So this is the receiver device. It does not have to point to the lamp, just to an area that's illuminated. Let's pretend this is 2 kilometers apart, and there's a telescope here. I actually did that with a telescope, and it works pretty well. So, demo time. Yeah. So this is the infected device, which will be running the malicious code. So first, I'm going to demonstrate how does it look without the stealth part on. So this is a light just blinking. There's not the blue channel implementation is not in this version, so you can see. This might not be a problem if you are exfiltrating data out of a place that there's nobody there or there's nobody seeing. It might not be a problem. Hopefully, when you click the start button here. Yeah. Hopefully, the program will start to decode the information if the light is blinking. So Murphy is playing tricks on me again. It's okay. I have a video demo also for this, but I wanted to show. So the problem here is that there are a gazillion Bluetooth-enabled devices in this room, and the software sometimes has trouble finding the camera. So the information that we are trying to exfiltrate is WOT, W00T, and you can see on the bottom left that it's already started to pick up the word 00T exclamation mark. So this is without the stealth mode. So now I'm going to try and use the stealth mode to see if you can notice any difference in the blue light. So it's connecting now, and it's trying to connect to the light bulb. Sorry for this boring part. There's no other way to do it except video. So what's going to happen is that the software is going to change just a slight variation of intensity in the blue channel, and the receiver part will try to adapt. So it measures all colors channel, it filters the images to a grid, and extracts the blue channel, makes an average of the colors that's seen, that determines the maximum color and minimum intensity, so it can auto-adapt to any intensity and variations in light, even during daylight. So this is the theory. In practice, sometimes it's a bit harder. Yeah, it's trying to decode something, but not very successful. But I can show a video later if we have time. Also, after the talk, I'm available, and I'll do the demos. If you want to talk to me, I'll do the demos too, so you can see. So, first failed. The penguin was not enough. So I'm going to tell you another tale. This is about Android. So Android, yeah. Damn it. Sorry about that. So I'm going to tell you another tale about Android. So, as I said, I like to research a lot of stuff, different stuff, and my overlords are awesome. So, one of the things that I wanted to research was a particular brand of Android devices. The audit turned out not to be so profitable in terms of bugs that I found, so I moved on into a full Android OS audit. At the point in time, it was Android 6.0. I've done that before with some success, so I know what I was going to look for. I usually look for permission bypass mechanisms or some logic errors, some logic bugs, and not the traditional bugs. And I look for opportunity to make the device behave in ways that are not expected. So during this audit, I found this package called NFC adapters and a function called enable reader mode. We'll get back to that. I'm just going to talk a bit about NFC really fast. So NFC stands for Near Field Communication, as you might know, and it's a set of communication protocols that enable two electronic devices to talk to one another if they're really close. So really close because the NFC involves always an initiator and a target, and usually this target is passive, has no batteries, so it has to be quite close to the initiator to use the energy of the transmission to process whatever it has to process and reply back. So it operates on the radio frequency of 13.56 megahertz, and usually a device can be a smartphone, can be a reader or a writer, can be configured as different operating modes. The modes just concern modulation methods, coding schemes, and protocol initialization processes. So back to the NFC adapter class. So while I was doing the audit, I noticed that there was no protection in this particular function. So when you use Android, for those who have Android, they know you have to give permission when an application wants to use certain resources on your phone, like the Wi-Fi card or like the NFC, for example. And I noticed all functions were protected by NFC permissions, but not this particular function for some reason. So I was curious. I wanted to know what this function does. What is it for? So what I did was I set up the software-defined radio and turn on the NFC on my phone and just analyze what's going on. And what's going on is that when NFC is turned on, there's the radio card is configured for a normal, usually type A pooling, which means that your device is always sending a packet, so to speak, is always sending a pulse of energy, trying to figure out if there's some passive device nearby, like a smart card, or like the card that you use to enter your door in this hotel, for example. It's NFC. So I discovered that I visualized the different modes of operation with the software-defined radio, because that's what that function does. That function allows an application to configure the NFC radio, even that if you don't have permissions. You don't have to have permissions to configure the radio. And what I figure out is that when you change the mode of operation to NFC type F or NFC type A, what the device does, it immediately starts to pull. It configures itself for this new mode and immediately starts to pull for new cards nearby. And there's this special kind of operation mode which is called skip and def check, which makes the radio card go silent. So the NFC does not pull anymore. So this gave me an idea, of course. So what if you can cycle through these modes really fast? What will happen? And do you see any problem here? So what's happened is then you get this NFC controllable bursts. You're not using NFC per se. You're not using functions of the NFC library to transmit NFC data in the traditional way. You're just turning on and off the NFC radio. And this results in a burst of energy because it's the NFC card trying to pull for smart cards around. So the timing is not completely controllable because it happens on the background on the phone. You don't have real-time control about it, but it's close enough to think and implement a data exfiltration method via these bursts. So on-off keying was the immediate idea, like burst, no burst. So the implementation that I did is that a radio burst stands for binary 1 and silence for binary 0. It's the simplest forms of amplitude shift keying, O key. So the protocol is a bit more complicated. I wanted to add Hamming 7/4 correction codes for the transmissions because there's usually a lot of noise, and I wanted to be able to receive that data properly. And this is the transmission part. So the transmitter is just your device that has been compromised by malware. We also tried some NFC USB tags. They're also interesting. So, but this is the emitter. So how can we receive this signal? Do you use SDR decoding? Do you code GNU radio? Do you use custom hardware? Well, if you remember 13.56 megahertz, this is also called high frequency band or short waves. So if you buy one of those expensive radios, you can actually receive the signal. But also if you buy a very inexpensive radio that supports for shortwave, usually almost all AM radios do, you can receive these waves. So I coded the receiver as an Android app, that's connected via the mic jack just to a standard, very cheap radio. So you can use the radio receiver, and you have a practical low-cost receiver with off-the-shelf components. Again, our main target to do this kind of research. So now you end up with an ultra-long-cost, long-range NFC data exfiltration mode. So long range, NFC stands for near, right? It turns out that no. If you remember about the pooling process, the initiator has to send some sort of signal. That signal cannot be weak because you have to power up a passive device. The passive device has to use that energy and then has enough energy to reflect back and still be readable. So it's sort of a strong signal. And we are thinking about data exfiltration one way. We are not thinking about making NFC work. We're not trying to make the normal NFC protocol to work. We're just using NFC, and we are trying to detect the existence of an NFC pooling process. This is important. So we got more than 4 centimeters, which is the standard distance for a car to work. How much more? Any estimate is? No. So we got successfully detected NFC over 40 meters distance just using a standard radio. Not a very expensive radio, just a standard radio, no dedicated equipment whatsoever. If we are talking about USB NFC dongles, we can detect that over 100 meters of distance. So NFC used like this is definitely not short range. So the attack scenario is quite similar to the attack that I showed you. So there's this compromised device that has no permissions or does not want to use the standard ways to exfiltrate data out. So it uses NFC on the device because it has a NFC chipset, and on the attacker on the receiver end just has an unconspicuous AM radio connected to his smartphone, and he's able to decode information out of it. So now for the demo, if you bear with me just a bit. So this is the attacker. The application is called NFC Drip. The plan is to open source it, and then you can play around with it. So this is the emitter part. I'm just going to put it here. Unplug this. And let's see if it works. So do you have the image? Yes. Okay, so I'm going to use one of these radios here, which is the cheapest ones I could find for this demo. I also have an expensive one that will allow you to listen to the NFC signals. It was not very smart to try to do this demo because I wasn't aware that this building is controlled, everything is controlled via NFC. So there's a lot of noise. I'm going to show you the amount of noise that there is. This is supposed to be static. Can you listen? Okay. So let's see what Murphy has for us. So I connect to the mic jack. I start the receiver. I power the radio on. It's just a standard radio. Start listening. And hopefully when I start the emitter here, it starts to send data, and you can see some spikes coming out, and it will start to decode whatever it wants to decode, which should be password. Okay. Maybe if I cannot put the antenna too much out. It's secret password with trees instead of e's. So it's detecting some errors, but it's mainly able to correct them, at least some of them. So you see the secret password coming out, and the demo gods were appeased this time. Awesome. So this is a short distance. It's around 1.5 meters, but it's enough for you to see that it's not 4 centimeters like they say. In a cleaner environment, you can use a much longer distance. As I said, we tried with also the USB sticks. We haven't have enough time to map out all the NFC radio chips that there are, and I'm pretty sure that they have different capabilities and ranges. There are some caveats, like the type of NFC antenna. This, just a second. So the NFC's antennas are a round coil, and this usually round or square coil, and this has some characteristics that makes it a bit directional. So if you want longer range, you have to be in the right direction because the signal is highly directional. Also, if you want to make antennas for this kind of signal, it's a bit harder. You cannot use like a standard bipole because it will measure around 11 meters, I think, for this waveband. So you have to have helicoidal antennas or other kinds of antennas. I'm not an expert on antennas or transmissions. This was just an experiment. So, still, conclusions. So, to win that will, ways are not wanting. So, I think the main point here is that imagination knows no boundaries. If a device is connected, and there's always be ways, there will always be people trying to get data out of that device or trying to break into that device. And just because someone tells you that technology works in a particular way doesn't mean that's implemented that way. It just means that people, when they thought about it, they wanted to do it that way. So the IoT, of course, brings extra challenges to security and also comes into effect these air-gapping processes and mechanisms. It makes no sense to have a completely secure building with, conductive ink to block from RF signals if you allow for your employees to bring a BLE-enabled light bulb into the office, and because they think it's cool. And last but not least, the statement here is that the NFC should no longer be considered a short-range channel. It can effectively be implemented a long-range data exfiltration channel using NFC, using low-cost equipment also. And that's it. So, questions?
Any questions in the room? People still not waking up properly yet. I don't know. Okay, well, experiment with the rest of the hotel.
Yeah, sure.
You could maybe report back later on what you're finding.
Yeah. Please feel free to reach me if you want a more close-up demo. I wanted to show the light bulb also working, but I had no time. Thank you. Okay.